So, hello everyone. Welcome to another episode of Quirkcast. This is Tim.
And this is Mikey.
And this is Sahil. So welcome everybody to a new episode of Quirkcast. Before we get started, if you're on the YouTube channel, actually I don't have to say this because we already said this from what you're going to edit out, so forget about it. um, so Tim, to get straight to it, I'm going to force an answer out of you on this question I have. I've been hearing a lot about forces since I was in high school. There's also a force of nature and a force to be reckoned with, and the force. What is all this? Like, explain this to me. What is a force? What's going on here?
Yeah, I feel like we have this kind of cartoonish, image of what a force is. It's kind of like in movies where you kind of have this telekinetic power. You just will something. You push your hand and some cup just fly away or something like that. But in fact, if you look into particle physics, the subatomic reality, is actually not that far off. So, but of course, macroscopically, it does not work like that. But in physics, we do have this concept called force. It's sort of a categorization of a particular type of interactions, and that involves So the basis of it involves something called a field, some kind of a force field. So the ones that everyone's most familiar with is probably electromagnetic field. So that's a force field, and this force field should be thought of as a property of space-time itself, and particles can participate in kind of feeling the force, so to speak, and through this force, it's kind of like a medium. They can push and pull and interact with one another. So I think sort of concisely, that's roughly what a force is in the particles physics sense.
So to take a step back a little bit, could you explain what a field is? Like, how can I visualize that?
Yeah, I guess a field is pretty abstract. It's almost a little bit it's almost like yeah.
I guess what's an analogy, even if it's not like perfect? Like how can I think about this like as an analogy in everyday life?
I think the best way to think about it goes back to one of our recent discussions about the fact that if something exists, then it has some energy, and a non-zero energy sort of defines the existence of something. Right? Mm-hmm. If you take the energy of something and you bring it down to zero, then there's no sense in which you can say that it really exists. Sorry, what was the question again?
I guess, how do you explain what a field is, or what the analogy?
Oh, yeah. So a field you can think of as a substance in exactly, and I think you can exactly think of a field as a substance to the degree that you can think of energy being equivalent to existence. So it's like there's some energy in space, and it's stored in this substance called a field.
Wow. So am I thinking of myself like in like kind of a substrate, like a substance itself that I can't really perceive with my senses as much, or?
Yeah, or maybe. So recently I watched some videos on Feynman. Richard Feynman on YouTube, and I'm gonna kind of quote him slightly in that sense. It's almost like we don't have the right context to ask this question. It's almost like, imagine you ask a caveman, like a caveman asks you like what an airplane is. There just is no context because the caveman doesn't understand like really what an airplane is, right?
I think you understand what fields are, though, right?
Yeah, but it's almost like that's the starting point. Like the world is made of a bunch of fields. Like even space-time, to some extent, we'll talk about that later. It's a type of field. It's just a sort of location where we exist in, and I guess the concept of fields goes beyond that. Like just the fact that we exist. Matter exists.
I mean, we are fields.
Yeah, exactly. So by existing, we're interacting with this field. So a field is just sort of like the property of space-time, and that has energy that can interact with other things.
Yeah, so I guess Sahil, you can think of fields as the clay by which everything in the universe is made.
That is quite a sophisticated piece of clay that covers the entire universe.
Yeah,
Okay,
I mean,
so
we've seen.
oh no, go ahead, Mikey.
Oh yeah, just to add to that, I would say, as far as we know, it's many different varieties of clay, but we think it's all really the same clay underneath.
Yeah. So going back to what you were talking about, Tim, you were so taking this field as if something as it's permeating all of space-time, and you mentioned space-time as a field. I guess like where does this tell us in terms of force? Like what how does this relate to force?
Yeah, so I would say, so first of all, like everything we see, pretty much is made of fields, quantum fields, to be more precise. And forces, they come under a more specific type of fields. Probably, I guess you can put it, you can say force fields, I suppose. And these are special type of fields, and they have certain types of universal. I guess we can cover that a little bit, yeah. So
Yeah.
the kind of the high school concept of a force is sort of like you push the wall and you feel that push, and the wall also feels it. That's sort of like a macroscopic type of a force. And in fact, Newton himself struggled a lot with the concept of gravity. His thought was that, if the sun is pulling the earth toward the sun, like how does it do it through vast amount of space and sort of instantaneously? Right? It's sort of kind of strange that, hey, the sun says, hey, come closer, Earth, and the Earth just immediately come closer. Like, what if the sun were to disappear immediately? Like, how, would the Earth still feel the force and whatnot? So these are problems that Newton faced, and then Einstein came along and kind of modified this idea. Einstein says,
Well, yeah, sure. Wait, well, okay. Before we get into that, we should, yeah. So this idea that a force is something that you can pull with a string, for example, right? When we say we're exerting a force, I'm like dragging like a bucket of hay or something. I'm pulling it with a string. We saw problems in high school physics where you calculate the amount of force that would be needed to drag this bale of hay, right? And we also learned that definition of force is connected to energy, right? If you remember, the derivative of the energy gives you the force. So really, it's if we describe the energy as like the fundamental substance of the universe encoded in these fields, and force is basically when energy is changing in a certain way. So that's really what force is at a fundamental level. It's the concept of change. You also learn that force is the derivative of the momentum. So force can be identified, one surefire way to identify when a force is being exerted on something is if its momentum changes. If its momentum is not changing, then it's essentially in a state of complete stasis. It's equivalent to it standing still, actually. So yeah, force is really nothing more than a change in the state of a system.
So I guess then how does this sort of tie back to I guess like fields, because you were explaining this in like the high school context, but if we are to, but I'm assuming it's not that, because that's a macroscopic description. So what is actually going on when I like push against the wall?
Okay, so that's what Tim was about to get into. So what is the mechanism that creates this feeling of force, which is essentially a change? There are a variety of mechanisms. Like how does the Earth go around the sun? Does the sun have a string tied to the Earth that's pulling on it? Turns out in a sense, kind of yes. It's not a physical string, but it's a string made of fields that are essentially tying them together. And okay, I just had to get that in there before Tim went.
Yeah, I mean, from the particle physics perspective, we always like to think of it in a reductionist way, at least part of particle physics. So we, to dissect the problem, we kind of have to look at the fundamental particle level. Like when you push something, really what is going on? More deeply, what's happening is really the particles themselves are interacting with one another. And we know that, for example, when the sun is, when the Earth is getting pulled by the sun, these are ultimately the average of many, many particles interacting and resulting in this tug of force we call gravity. So individually, on the particle level, a force is really coming from interactions. And we know from Einstein's theory that interaction doesn't happen in a vacuum. We cannot just have two particles far away interacting. Interaction has to happen when something is in contact, right? So force fields kind of provides this medium for this contact interaction.
It's more like sending a signal, right?
Yeah. It's like sending a signal and also storing it. It's almost like a particle says, hey, I need to change my momentum by this unit or change my energy. I'm gonna encode that into the force field, right? And those energy and momentum will propagate inside those force fields. So the force fields they themselves have energy and momentum. And in the future, maybe those will be absorbed, released by another particle as another particle interact with those force fields. So microscopically, I think that's a better picture of, a more accurate picture of what a force really is.
Huh. So the way I'm visualizing this is like you have a bunch of particles, like take the interaction between, well, maybe there might be a correction to this, but take the interaction between like the sun and the earth. And they're like all these, I mean, there's empty space, but there's stuff coming in the empty space and all these fluctuations happening. And then you have like, is it kind of like a messenger sort of thing, like gravitational, like waves or gravity or whatever is going through this space, through all these quantum fluctuations, and then reaching the earth, and the earth is also sending its own gravitational, I guess, like message to the sun, and they both are interacting, and that causes the orbit. I mean, given initial conditions of it orbiting around, but is that something like that? Is that how I should think about it?
The messenger analogy is absolutely appropriate.
Thank you.
Look, we have a name for that. These are the mediators, right? The force mediators.
Yeah, technically they're called mediators, but
yeah. So pretty much all the forces we see in nature, and I guess we can enumerate them. There's the electromagnetism, there's the weak force, there's the strong force, and there's gravity. Every single one of them has some sort of messenger, like you mentioned, or mediators that are responsible for carrying this message and kind of, ultimately lead to these macroscopic forces, the tugs and the pulls and all that.
So the question of how many forces there are is really a question of how many species of messengers do we have.
Yeah. Well, actually, I wanted to ask you, Tim, and sort of, I mean, I take that for granted, but how do you know that that's the case, where a force is exchanged by like two particles, like it's represented by a particle? Like, how do you know that, or what goes behind that, thinking of it like that?
Yeah. Let's see. I think that.
Well, there's experimental evidence you can do, right? Like if you can do the equivalent of having the sun disappear by taking out it really quickly and measure how long it takes for the effect to be felt, and it's proportional to the distance that a messengers would stop sending signals at.
I mean, it's more like, I guess you test it at colliders, right? You try to zoom in and to see what is the smallest interactions you see when you kind of move away, or when you zoom in one particle at a time. How do they interact with one another, and depending on the energy? And you see that when that happens, it's really a very discrete kick, right? It's like particles come in, they get a kick, and then it's done. That's one interaction. So then, and then the math checks out, it matches with experiment. Then we know that the real life experience is really an aggregation of many of these kicks let's put it that way, the average of many of these in a quantum mechanical way, and then you feel like this tug and pull, basically.
Yeah, you can literally, if I imagine like a positive and a negative charge attracting each other, I can literally imagine that there's a stream of messengers between them communicating that force at a finite speed, right, at the speed of light. And that leads to very particular predictions about what happens if I move this charge away suddenly, right? There's some time delay, and then eventually this responds to the new distance. And if you have lots of objects here, you can actually model that. It literally looks like a fluid, right? Moving in response to something changing in a time-delayed fashion. And it literally has a frame rate. Even you can literally calculate the frame rate of the signal. It's on a Planck scale, but.
So one question I have, and let me know if this is like involves too much explanation, but if I think of like the electromagnetic force, like think of two electrons coming together, they exchange a light carrying particle, the photon, and then they know to repel each other. But if I like take certain other kinds of particle interactions where particles like decay into other things but emit these force carrier particles, how do I think about that in a similar analogy as like a force? Because nothing's really like moving. I mean, just decayed into something. Like particles decay into other particles and may emit force carriers, right?
Yeah, let me try to take that. Yeah, so what you mentioned, when particles attract one another, there's sort of this notion of change in the property of a particle. So the most basic change is a particle can emit a photon and get a kick, right? And this is sort of like a change in, I don't know, their space-time property. But it's also possible to have a...
Wait, also that kick, by the way, just in case it wasn't clear, is what we think of as the normal electromagnetic repulsion or attraction. That kick it gets when the photon...
Yeah. Yeah, but there can be a more sophisticated, convoluted change. Is that the type of particles could change. For example, if I stay in it, quarks have this extra property called color. So a quark can be red, green, blue. Has nothing to do with actual color, but it's just that there are three types of charges. And as they get a kick out of emitting a gluon, their color property could change, right? So in the same way for decay, really what's going on is that when it emits or absorbs a messenger, this extra property, the type of particle also changes. So an electron can change the neutrino, a proton can change into a neutron, and vice versa. But the details, lies in the subtle ways these different these force fields have slightly different properties. And we can get into that. And for weak forces, they're massive because of the Higgs mechanism. We haven't gone through that yet. And the strong forces are a little different, and the electromagnetic forces are different, and also gravity is different. So.
If I think about it, I really take issue with the statement that there are four forces of nature, because there are actually never four at the same time. Because the weak force is not a force, technically, at the scale when you increase the temperature, then electromagnetism stops being a force, and the weak force essentially becomes a force. So they kind of switch.
Yeah,
there's never four at the same time.
It's almost like this weird categorization, right? It's almost like when you were a kid, you learned that there are three phases of matter, like water, liquid, solid. But that's a silly categorization. It turns out that
that one at least has some practical value though on Earth. I can get that, but this is actually wrong because electromagnetic force and the weak force are actually the same thing. They turn into one another.
Yeah, I mean we can go into
and
that.
And the two never exist at the same time.
Yeah, I mean that's one of the great works. I think the electroweak unification. One of the pioneers in the electroweak unification, Stephen Weinberg, has recently passed away, but then his work was very much celebrated. So the idea is that the weak force and the electromagnetic force are really one and the same force. It's just that there's this Higgs field, and the Higgs field is kind of a troublemaker. It kind of got frozen as the temperature cools, and it kind of messes up part of the forces of this electroweak force. So that's why these decay become that, and as such, it gives masses to some of these force mediators, and that messes up the properties. That's why the weak interactions is very different from electromagnetic interactions. But ultimately, they're one and the same. And if you heat up the universe to extremely high temperature, they would just appear completely identical.
Wow. So what you're saying is that there are difficulties because in the weak force, there are these force carrier particles that have mass, unlike a photon, which is massless, and that presents difficulties. And that's where this Higgs field mechanism, Higgs boson, kind of comes in.
Can I just summarize it in a simple way? I think so.
Yes, please do.
So I guess the story goes that at the beginning of time, you can think there's three forces: gravity, the strong force, and the electroweak force. But as the temperature dropped down, something froze. The Higgs field froze, and that was like a fly in the ointment that essentially broke the electroweak force. The electroweak force was a big force, and it got broken by the Higgs field when the Higgs field freezes, and most of it stops being a force, but a small piece of it survives, and that's what we call the electromagnetic force, the small piece of the electroweak force that survived. And the relics of that, the remnants of that process, are what we see as these massive force-carrying particles. But if they're massive, they're not really force-carrying particles.
So I want to make sure I understand this, or make sure I understand like what you're trying to say. So when you say electromagnetism and the weak force, currently in the state of the universe we have, they're two separate things, even though at higher temperatures they're the same thing. They have two separate force meeting particles. Electromagnetism is the photon, and then weak has the WZ bosons, but I don't want to get into that. But when you talk about like the unification of these two forces in electroweak, are you saying there's one kind of force mediator particle that's there and not like two? Or like, what does it mean for them to be the same?
There aren't two. There was one, and they were all one big happy family. And then when the Higgs field froze, three of them got killed, and then one of them survived. And the three that got killed are the remnants of that are these massive particles that we see.
Yeah, I mean, you could think of it as separate particles, but in the same way, it's almost like if you look at gluons, right? The mediators for the strong force. There are technically 8 types of different gluons, all with different colors. But we don't think of them as different. It's just that their colors, they just have an extra property that could vary. So pretty much the electroweak interaction is like that. The WZ boson and the photon, in the early days of the universe, they're all the same. They just have this, I guess we can call it the weak color. Or you can put a label on it, the weak charge. They just have slightly different weak charges, but they're really the same thing. But then once, like Mikey said, once the Higgs field froze, pretty much, like three of the 4 weak forces just died, pretty much. They got heavy. And when they got heavy, it means that the force field is not accessible anymore. It's like you can't feel the force anymore because it's so heavy, it's all stuck, right? And then you can't access it anymore unless you try really hard. Then the only real force that's left, it's sort of like the electromagnetic force. And that's why we don't feel it in every day. You don't feel the weak force pushing you. When you push, you feel electromagnetic force, right? You don't feel the weak force. And that's because it's frozen. The force field is frozen. You can't feel it.
Gotcha. So I want to return back to what you were mentioning earlier, Tim, about space-time being a field and how that's connected to forces, and that particles can feel these forces. But like, how does that all connect with space-time?
Yeah. So this, to understand this, you first have to understand kind of like a geometric picture of force field. So force field kind of have, if you look at the electromagnetic force field, it does have some unit, like how strong the force field is, like the electric field or magnetic field. You can measure it with a compass and whatnot, right? And in a very real way, these are kind of like extra dimension in some way. These are actual extra properties of space-time, and that's why in this way, the direction of space-time, like, you know, up, down, left, right, front, back, these direction, you can also kind of think of them as fields. These are like fields of directions or fields of how space-time is jiggling, right? And if you think of it that way, then this analogy is complete. You know, space-time, if you think of them as a force field, it's a field of the location itself. And if you walk through the math is very similar. In the same way, because everything lives in space-time, you're forced to participate in gravity. And that's why, that sort of, and this bit kind of explains a little bit why gravity is so universal. Like everybody participate in it because gravity is a force about the space-time field itself. So.
Huh. So are you saying we can think of, I guess it's kind of like, not really tautological, but it's a field of locations themselves that is gravity. It's like gravity is I'm trying to internalize this.
Yeah, I mean, gravity is a bit special. I mean, that's one way of thinking about it. The stretched out space-time is itself is a field. So I don't know.
Yeah, it's almost like you're in a cartoon movie, and then you realize that like the fruit you're eating is like a cartoon fruit, and then you realize that like the road you're walking on is a cartoon road, and then you look out and you notice that like the whole thing, the whole fabric, everything's painted on is a cartoon fabric.
But in some sense, it's almost more natural, right? Like we know there is space-time, and we know there are forces. It almost begs the question, like why should we have something extra? Why shouldn't everything just be space-time? Maybe, you know, or maybe we wouldn't call that space-time. Maybe just one thing, you know, in this way of unification. Maybe everything is one thing.
Huh. Wait, then how do I think about the other forces? Because if gravity is space-time, like where does electromagnetism fit in, or electroweak?
Yeah, I think personally, I would believe that ultimately, electromagnetism and all the other forces, they are probably part of gravity as well. Ultimately, like it's just because of the particular shape of our universe that we see them slightly differently. Just like how the electroweak forces, you know, the weak force somehow seems different from electromagnetism, but it's just an artifact of the way our universe is. But I think personally, probably everything is ultimately space-time in some ways. Maybe we wouldn't call that space-time anymore. I don't know.
Yeah, I mean, there's some. It's an intriguing idea, but it's also like one that people have been thinking about for a long time. Actually, in the 1930s, people wrote down simple mathematical models where you start with high dimensions of space, and when you squeeze out these higher dimensions down to the three spatial dimensions we see. The byproduct of that is something that looks like electromagnetism. So it's like gravity in the dimensions that got kind of squeezed out.
Wait, what do you mean dimensions squeezed out? Like, I'm like imagining hands kind of wringing like whatever you call space-time and just
so like,
squeezing out the other dimensions.
Yeah, I guess one of the things that dimensions can do mathematically is collapse. Or compactify and shrink, which is equivalent to collapsing. And when the gravitational field essentially, you know, in the situation where a dimension gets wound up and shrinks down to zero, so it disappears, that's one way to get rid of a dimension. If the gravitational field in that direction kind of gets wound up in that direction, you get a structure that looks like a lot like electromagnetism at low energies. And when people first wrote down these models, I thought, oh man, this definitely must be, you know, everything must come from gravity. But then they had some trouble getting it to work with the other, like the electroweak force and the strong force, but definitely some intriguing hints there.
Yeah, it's a lot more complicated than that, but personally, I would believe in it. It's complicated, but probably in some ways it will work out.
Yeah.
So we're a little bit over time, but do Do you guys want to have any closing thoughts before we close out? Mikey, you're
Everything.
smiling. I'll let you go first.
It's I just like the fact that it's going back to the theme that there's really just one thing, energy, that gives rise to existence, and changes in this energy field are caused by force fields, and it all kind of jives with a lot of the concepts we learned in high school, but it's kind of a more unified picture, I think.
Yeah. I suppose I'll go back to some references in Star Wars. Even though I'm not really ultimately a big fan of these movies. I mean, obviously the physics is not sound, right? You can't just push and pull, but you know, it's funny how reality fundamentally is actually not that different, and the way we're talking about forces, like I don't want people to get the impression that, oh yeah, there's some like four is like a magical number, it's like 4 forces and whatnot. Just like how, you know, different phases of matter, right? People learn that there are 3 phases, and then there's plasma, and then now there's like hundreds like topological phases and whatnot. In that same vein, probably there's nothing special about our 4 forces. You know, of course the concept of force is special. There could easily be more, right? And then all these forces could easily fit into some unifying pattern, right? And then I guess in a human way, we can all think about that. You know, ultimately we're all interacting with one another through gravity, and that's no denying, and through other forces. You know, it kind of gives you this connection. I don't know, it's a nice thought. Let's put it that way.
Well, cool. On that note, I'd like to thank everybody for joining us, and we'll see you all next week.
Yeah, see you. I guess may the force be with you all.
Yes.
All right, see you guys.